I thank the organizers for giving me this opportunity to present my work I've been doing in last few months at IIT Bombay, and my collaborators are Dr. Nishita Desai from TFR, she's a postdoc there, and Professor Sumiran Pujari, a supervisor at IIT Bombay. So I'll briefly outline what I'm going to tell you today. Firstly, I'll talk about briefly about deconfined quantum criticality, what it is, and then I'll highlight few earlier studies, and uh, and then briefly introduce our model, and then I'll discuss the results for our model, what we have obtained. So, as we all know that Neal state is an antiferromagnetic state that breaks this rotational symmetry in general SUN, uh, which is of course sensitive to quantum fluctuations and the low energy excitations, as well as continuous spin waves. And valence bond state is actually a product of quantum fluctuations. When you introduce in this Neal state, you see a system going into this singlet pairs. So yeah, uh, the excitations here are localized triplets with confined spinons, and so deconfined quantum criticality is all about this critical region between this Neal to VBS transition, and uh, critical region of interest associated with Neal to VBS transition in this magnetic systems, and where you can actually see the deconfined nature of spinons in this region. But the question is why it is so interesting. As you know that Neal and VBS, from the Landau-Ginzburg Wilson paradigm, we all know that ferromagnetic state actually breaks this rotational symmetry, while para doesn't, and you have a phase transition between these two that is accompanied by spontaneous symmetry breaking this phenomena. But in for both Neal and VBS, you see that they actually both of them break this some of the other symmetries. For example, Neal breaks the rotational and VBS breaks the lattice translation symmetry for spin half systems. So the question is whether can we have a continuous phase transition for such a scenario. So let's from the naive LGW paradigm, when one can expect that it should be a first order or maybe a coexistence of two orders, or maybe beyond can we have a beyond LGW scenario. So I'll just briefly highlight what LGW scenario, paradigm is all about. We have a order parameter description of phases, and then you have in due to symmetric breaking, you have a emergent gauge field and deconfined gauge degrees of freedom that is emerging from this fractionalization of the order parameters. So this is sometimes also referred to as beyond LGW paradigm. But I'll highlight few studies before 2015 where they have shown to, this transition actually have to shown to have a second order phase transition, surprisingly. Some of them are by Anders Sandvik as well, and 2007, where continuous phase transition has been found in these systems. Till 2015, you have many studies focusing on this continuous aspect. But after 2015, the senior has been completely contrasting, where you have start emerging, where you'll see some emergent physics coming into the picture. That is because of breaking S of I symmetry. Maybe you have these two phases getting manifestly inherent in your system. And also you have first order studies that is being more prominently being arising in your this sort of scenarios. So in our system, uh, there are, I can give you numerous studies where people are more seeing first order transition in this system. But our approach in for this model is all about this system, one particular paper where they have continuous phase transition studied for SU and general models, where they vary this parameter n and then see this Neal to VBS phase transition. So we will actually try to recast this problem into a spin-1 problem and fix the symmetry SU3, and then see if we can get this continuous phase transition in such a scenario. And not only that, we'll also see this physics under reduced symmetric conditions. If we give some perturbation like Heisenberg perturbation, like SU2 perturbation, can the deconfined critical bit be tuned? That's the question we are going to ask. So I start with basic SU3 symmetric Hamiltonian. So this Hamilton is SU3 symmetric, one can show that. And then I'll add perturbation like SU2 perturbation and see what's the scenario. Uh, the first question that should be asked is, does the phases survive under higher spins, because I'm using spin 1, and if so, what is the criticality class, and what is the effect of this on this criticality class due to this SU2 reduced symmetric perturbation. So as I see, I mean, as we have seen, up to the system size of 64, we are able to get a scaling behavior of this order parameter Rn. These are Néel order parameters. In the lower part of this regime, this is Néel phase, and that's VBS phase. So clearly, these phases are surviving even for higher spins, and we also see a phase transition. Not only that, we feel this is a nice phase transition. When we try to collapse the data, we see critical exponents for this in the absence of perturbation as follows, which is very close to the SU3 type. So the issue is now resolved that we are able to see SU3 universality class of this phase transition in the absence of perturbation. We were able to answer one thing. The second thing is, if I put finite perturbation, what is the key scenario? Plots looks very similar, but if we try to collapse the data, the scenario is quite different. The neta dynamic exponent, for example, critical exponent, is reduced consistently, both in the Néel phase and the VBS phase. So this points out to some different universality class. Actually, this is SU2 universality class. When we try to fit in our data, actually we anticipated much higher JH value to be the scenario for having a SU2 universality class, but we never expected that this much small value of 0.05, for example, JH would give a different universality class. So we will have invested a lot of time in higher GH values, and then we are again coming back to collecting data between 0 to and 0.1, and then see if this universality class is same for for any non-finite JH values. So interestingly, from this paper by Block and Melko, we see that this value corresponds to this value, this SU3 class, and this value for the VBS order parameters. This is so this value corresponds to this value, that is SU3 universal class, and this value, this is around 0.2, corresponds to this value. So this is like to say that I'll come to the point. I mean, I have more plots to show, but I am in the, I have 2 more minutes. So before coming to conclusion, we have also signatures from this order parameter extrapolation, where in the first order you see that if the order parameters extrapolate to 0, then you will have a more confirmation that this is a second order phase transition. But apart from that, I mean, so this plot is for JH 0.0, and then this is for JH 0.1. Then you will see that the extrapolations going into the thermodynamic limit, the order parameters are 0, showing it as a second order phase transition. But at a finite perturbation, we start seeing that there is non-finite value that is appearing, which is a signal of first order phase transition. Not only that, we have also estimated these histograms where, for example, in this paper, they have seen weak first order phase transition for weak, I mean, for higher system sizes, you'll see that a double peak behavior in your order parameters, but we are seeing this unnormalized probabilities where we are seeing only single peaks, that is also signaling to a continuous phase transition. So in order to summarize, I'll summarize what I have obtained in this last few months, is that for in the absence of perturbation, I see a universality class that is of SU3 type, which is very naive to even imagine, and then which is very evident even from imagination. But you see SU2's universal class for in the presence of perturbation. So our results also show deconfined critical behavior within this range of perturbation, that is 0 to 0.1. And the take-home message is that the spin-1 particles can actually behave like two independent spin-half particles, like they are independent. in reduced environments. Like in this case, it is reduced symmetry. In experiments, you'll have nuclear physics scenarios. You can have this spin-1 particle behaving as spin-2 spin-half particle. Yeah, I'm done. Thank you.
Okay, questions?
Do you know what happens for the other sign of this Heisenberg term if you make it negative?
We haven't checked, but that is our next plan.
Uh, can I ask a quick follow-up? Okay, maybe there are other questions. Okay, so so for this sign of this Heisenberg perturbation, so if you put the JH to be 0, then nematic and the nail orders scale have the same scaling dimension. Okay,
Yeah.
so for this sign, which has a lower scaling dimension?
For this kind, I think here it is evident, right? I mean, Neil is always lower in this.
I see. This is very surprising.
Can you do the other sign of JH in your SSC? This JH is just minus the projector where you project one outside,
Yeah,
right? So can you do the plus? Won't you get a sign problem?
I think we'll have to rework the projector operator this thing in this SSC for the other.
I mean, can you do this thing where the other term has one sign and this term has one sign? I'm not sure.
I'm not sure. I have to rethink and I'll let you know.
Okay, so let's thank the speaker.